Awesome, thank you.
All right, our next speaker is Iain Moffatt from Royal Holloway. He'll be talking more about delta matroids, even if they're not in the title.
Okay, so thank you for sticking around for the next talk in this topological session and not running out after Carolyn's excellent talk on this. So I'm going to talk a bit about the critical group for embedded graphs, and everything today is joint work with Creil Marino from UNAM and Steve Noble, who's currently at Birkbeck, but will very, very soon be in Leeds with Dylan. Okay, so as Peter said, so everything I'm going to talk about is really a continuation of Carolyn's talk on delta matroids. However, I've hidden all of the delta matroids for the talk, so I'm going to kind of present this as just a talk on topological graph theory. And the reason I did this was, well, I looked at the conference title and, well, someone had to justify this term mostly, and I felt that was my job to do that. Okay, so where are we? I'm going to start off nice and simple, because we all need to get topped up in coffee. Okay, so I'm going to start off with a tree. So I've got a tree up there, and I'm going to take my tree, and I'm going to pop it in the plane. And I can make some rather straightforward observations about this, in that this tree has exactly one boundary component. So what does this mean? Well, if I stand beside an edge, and I just walk along an edge and keep on following, then by the time I'm back where I started, I've covered each edge, or both sides of each edge. Okay. So I've got one boundary component. Now, if I take this tree and I embed it in some other surface, so for example, I draw it in this yellow torus down here, nothing changes. It's still got one boundary component. Okay? In fact, if I draw this in a two torus, a real projective plane, it still has one boundary component. So the neighborhood of any tree drawn in any surface has exactly one boundary component. And if you're in the plane, this would uniquely characterize trees. However, in general, there are lots of other embedded graphs that have this property. So if I take some other graph in a surface, and I've got two examples here, so I've got this green torus over here and the yellow torus up there, and I've also drawn the nets of the surfaces here, so I'll often work with the nets. So this is a usual picture that you form your torus by just, taking your square and just closing it up so the arrows align. So you've almost certainly seen these pictures before. Okay, so what do I know about boundary components? Let's take a look. Okay, so my neighborhood of the graph is going to have some number of boundary components. So for example, with my yellow torus, I stand beside an edge and I keep walking, and I see my pink person gets back where they started, but haven't covered all of the sides of all of the edges. So I need to take a second blue person to stand and walk around there, around the back. And I see, okay, so this is going to have two boundary components, one in pink and one in blue. But on the other hand, if I look at my embedded graph down here, well, this just has one boundary component, so I could come down here, up here. That would take me to there, and then back along, and then I'm back where I started. Okay? So I've got some things that are very much non-trees that have exactly one boundary component. And this is the one definition you need to remember for this talk. I'm going to call these a quasi-tree. So a quasi-tree is an embedded graph whose neighborhood has exactly one boundary component. And these were exactly what Carolyn was talking, but I've just changed the language from ribbon graphs to graphs and surfaces. And the idea here is, again, what Carolyn was just saying, is that if I'm wearing my topological graph theorist hat, whenever I see tree in graph theory, if I want to think of a topological version, I'm going to think quasi-tree instead. Okay, so I've got this idea. So I'm going to start off with an initial problem. Okay, so first let me clarify what I'm working with here. So I'm working with graphs. They're embedded in oriented surfaces. So this is important. I'm only ever going to consider orientable surfaces, so sphere, torus, two torus, and so on. So I'm not allowed projective planes, like Caroline was considering this morning. And I do actually need an orientation on it, because I need to know what's clockwise and anti-clockwise. Forget about the cellularly embedded condition. You just want to see that there if you're a topological graph theorist. Okay, next up, so we all know what a spanning subgraph is. So it's a subgraph that contains all of the vertices of the original graph. So I've got my embedded graph here, and I've got a couple of spanning subgraphs on the other side. And I've drawn these both into the sort of donut picture and the net of the surface there. So my spanning subgraph is either a quasi-tree or it's not. So it's either got exactly one boundary component or more than one boundary component. So for example, if you look at the middle embedded graph, I see, okay, so this has got two boundary components. So this is not my spanning quasi-tree. However, the other example, I can check this has exactly one boundary component, so this would be my spanning quasi-tree. So that's good. So I've got my embedded graph. Some of its spanning subgraphs are quasi-trees, some of them aren't. And as a group of combinatorialists, what do we want to do? Oh, let's consider the problem of counting these. So the setup, so if we're given some embedded graph, we want to just count the number of subgraphs that are spanning quasi-trees, so spanning and without exactly one boundary component. Okay, so this is a very nice combinatorial problem, absolutely valid in its own right. However, I'm not really interested in it for the combinatorial problem in itself. So what I'm really interested in is coming from the critical group. And there's a huge amount to say about the critical group, and I'm going to say almost nothing whatsoever about it. So I'm going to just be very, very basic in my understanding here. So my critical group, what is it? It's a finite abelian group associated with a graph. So rather than a definition, I'll give you some examples. So the critical group of Cn is Zn, of K4 would be Z4 plus Z4. Other thing you need to know is it's interesting, okay? And it pops up in several places in mathematics. So most famously, it would be the group of critical states of the chip firing game, or if you're a physicist, the sandpile model pops up in parking functions and lots of other places. So it's a genuinely interesting mathematical structure. And my motivation for what I'm doing today is really that there are some very nice properties about the critical group. And what is a critical group? It's a group of an abstract graph. But these very nice properties, they actually require you to consider plane graphs. And moreover, they require you to take a plane embedding. So what's happening is you've got topology coming into a situation where it shouldn't really be there. Okay, so what do I think as a mathematician? Well, clearly, maybe we're missing some part of the picture here. There's some topology is creeping in and we don't quite understand where. So I want to understand that. And there's a question about, is this really about a result about critical group of embedded graphs rather than abstract graphs, once you start getting these plane conditions in? So this is a question I want to answer, and the first thing you need to address is, well, first of all, is there actually a critical group for embedded graphs? And this is really the starting point for what I'm interested in. Okay, so the first step is I want to define one, and I'm just going to take you through the thinking about this today and the philosophy. Okay, so I want to define one, so where do I go? Well, I go back to the definition of a critical group, and I go to probably what's the most common definition. So I'm going to grab my graph Laplacian. So I'm just pulling adjacency information from the graph, encoding it as a matrix. It's reduced, so I'm just knocking off a row and a column. And the critical group, it would be defined as, so you take a number of copies of Z and just quotient out by the ideal generated by the rows of this matrix, this reduced Laplacian matrix. Okay, so that's great. But this doesn't really necessarily help me straight off, because this is a good, honest graph theoretic definition. The matrix encodes adjacency information. It doesn't really encode anything topological. So I have to think about where I can find some angle in there. And the other observation I can make is that, well, where else do we know the reduced Laplacian? Oh, we know the matrix tree theorem. So the determinant of this reduced Laplacian is going to be the number of spanning trees in a graph. Okay, so what have I got? So my critical group of a graph is just obtained by quotienting out by terms coming from a matrix that counts trees. But what's my general principle when I change from graphs to embedded graphs? Trees become quasi-trees. So my idea is, well, I'm going to try and define a critical graph for embedded graphs by finding some matrix that counts quasi-trees. So something that plays the role of the reduced Laplacian in the bottom. So that's my approach, that's my line of attack. So let's find a matrix quasi-tree theorem. So a version of the matrix tree theorem for quasi-trees. So I want some matrix, I want to construct some matrix whose determinant will give me the number of spanning quasi-trees. Okay. Now, for the moment, I'm going to restrict to one vertex embedded graphs. If I was working with graphs, that would be kind of a big assumption, restricting to one vertex graphs. But for topological graph theory, that's actually not a big restriction, because all of the topology really is encoded in the loop structure. So I've got one vertex embedded graphs. And I want to construct this matrix whose determinant is the number of spanning quasi-trees. So the first thing you have to do is recognize quasi-trees by a matrix. So I want to find some matrix from this embedded graph, and I need a way to recognize the quasi-trees. And I think, well, okay, so how on earth do you do that? Well, fortunately, this has been done in various places in mathematics. And I first met this back when I was a PhD student in this paper on quantum knot invariance. And there's one of the main technical results in there is this theorem, and it sort of relates the GLN weight system to the determinant of some matrix. And what I'm able to do is just translate from this language of weight systems, whatever they are, to embedded graphs. And this gives me exactly the matrix I want. So let me just tell you how to do this matrix. So you've seen it. I don't expect you to memorize this construction. So we've got our one vertex embedded graphs. This will be my running example here. So I've got the torus picture, so the donut picture, and the net. So I think I'll just work with the net of the surface, because that's going to be a bit clearer. Step one, I just arbitrarily direct the edges. So I've made a choice. In the end, it's not going to matter. You get different matrices, but it will work out. Next up, I'm going to take a square matrix indexed by the edges of this embedded graph, so A, B, C, and D. And then I've got this kind of complicated rule that tells me whether an IJ entry is 1, -1, or 0. So let's do this with some examples. So for the AB entry, what I'm going to do is I look at the subgraph on edges A and B. And I just travel round the vertex in the direction of the orientation, and I notice I see head of B, head of A. Tail of B, tail of A. So I see head, head, head B, head A. So that tells me my BA entry will be a +1, my AB -1. And I just keep doing this for as long as I've got. So I go around, I see, what am I doing? I'm doing head of A, head of C, so my AC entry will be 1, CA minus 1, and I keep going like this, and I fill them out. Oh, and something that might happen is, well, here I'm going head, tail, so this doesn't fit the pattern, so I'm just going to throw in a 0 for my DC and CD entries, and I've filled out my matrix except for the diagonals. What do with the diagonals? Pop zeros in there. And then this knot theory paper just tells me that the determinant of this this matrix is non-singular if and only if I started off with a quasi-tree. You could prove that Poincare duality if you like. And it turns out that actually you can kind of find this theorem in different language in other places as well. So you can go through the delta matroid world, and with a bit of work you can actually recover it from work of Boucher on delta matroids as well. It's probably somewhere else. I suspect it's in a few places in different language. Okay, so how are we doing? Where are we? Okay, so we've got this matrix. So let's look at the matrix. We're leaving embedded graphs and working with the matrices. Okay, so we've got this property. So our matrix is non-singular if and only it's a quasi-tree. So that was just from the last slide. What else do we know? Oh, when it's non-singular, the size of the matrix would be twice the genus of G. Okay, so why on earth is that? So that's not actually a hard observation. That's just Euler's formula. Quasi-tree, I know the number of faces, it's 1. I know the number of edges, that's the side of my matrices, and I know I've got one vertex, so V minus E plus F is twice the number of connected components minus twice the genus. Other observation, very basic, straightforward one, is if I take a principal submatrix, so for example, if I'm taking the principal submatrix on the elements B and D, so I just restrict my matrix to the entries in the rows and columns B and D, well, that's also the matrix I would obtain if I just restricted my embedded graph to the entries B and D. Okay, and this is just true by, it's an observation, it's true by construction. So this gives me a reformulation of a problem, is that we want to count the number of quasi-trees in G, so instead of that we can just count the number of non-singular principal submatrices in B. So let's do that, but for that I'm going to make two more algebraic observations. The first is that B is skew-symmetric, obviously, by construction. The second one is a principally unimodular matrix, or PU matrix. So this means that the determinant of any principal submatrix is either 0 or 1 or minus 1. And that's all that can happen. That requires a proof. That's not trivial. You have to do a little bit of work to find that, to show that. But it's true. Okay, so let's take these facts forward. So we've got a PU matrix, skew-symmetric. What do we know? Oh, it's skew-symmetric, and we know the determinant is the square of the Pfaffian. And we also know the determinant is 0 if M is of odd order. Basic matrix facts. If I take the characteristic polynomial, so usual definition, so determinant of Ti minus M, maybe an exercise you could give maybe your advanced class in linear algebra, your graduate class, would be showing that the characteristic polynomial is this alternating sum over the size I principal minor, so the principal minors, that's the determinant of the principal submatrix. Okay, so we'll take that fact forward. So our problem is we've got this skew-symmetric PU matrix, and we want to enumerate all of its non-singular principal submatrices. So we want to find this generating function up there. Okay, so I can just rewrite this. I haven't really done anything. I've just changed the expression into sum. So Tj times the number of non-singular principal submatrices of size j. But I can use my light orange and purple facts to notice, well, the determinant, because the determinant is the square of the Pfaffian, determinant must be either 0 or 1. So I can just get the number of non-singular submatrices just by adding up the determinants. Next up, I can use this or a dark orange fact here to replace my t to the j with some alternating sum, because I'm never going to get a -1 to an odd number. And then, oh, that's just this expression here with a little bit of normalization. So what I've shown here is that these non-singular principal submatrices are enumerated by the characteristic polynomial. So I can pull this in and bring it back to the topology. So I want to count all of the spanning quasi-trees, and I'm going to take T, I'm going to enumerate them with respect to twice the genus. So I want this generating function up in the corner. So I know I can just express this in terms of the non-singular principal submatrices, and I know that's the characteristic polynomial. So I get that the characteristic polynomial of this matrix enumerates all of the quasi-trees, or the spanning quasi-trees. And if I take t equals 1 in this, I'm going to get my matrix quasi-tree theorem, so the determinant of the identity plus this matrix B gives me the number of spanning quasi-trees in G. So if you want an example, so here's my B, my I plus B, and if I 4x4 determinant, I need to go into Maple to calculate that, and I'd find a determinant is 6. And this does indeed have the 6 spanning quasi-trees. So we're quite pleased when we found this, but we knew it wouldn't be, it must be in the literature somewhere, and we eventually tracked it down in that it's actually, you can deduce it by changing language from some result on Euler tours by Macros and Poulet from 1996. The characteristic polynomial result, I haven't been able to find that anywhere in the literature, the more general result. And maybe at some point I should make the comment that what I've really found is that I started with I was motivated by the reduced Laplacian, but this matrix is really an analog of the circuit co-circuit matrix rather than the Laplacian. But I won't go into that. Yeah. Yeah. Okay, so we've got critical groups. So our idea here was to quotient out by the rows of some matrix that counts quasi-trees. So we can just make this definition of a critical group, so this I plus B of G. And if I do this for this example, I would end up with 6 mod 6z. I know the order of that is 6, and this has got my 6 spanning quasi-trees. So by this thinking here, I've got some analog of a critical group. But, well, I call this a critical group, and you get into questions of, well, is this even well-defined? Because I did make some choices in the construction here. What if G has more than one vertex? What do I do then? Because I restricted to one vertex embedded graphs. And is this even the right thing to do? Yeah, and to answer these questions, you have to dive into the world of delta matrices and just pull out Carolyn's discussion. In this matrix B is really a real representation of the delta matroids of an embedded graph that Carolyn was talking about this morning. But however, each delta matroid has many different representing matrices. But these are all related more or less by a principal pivot transformation operation, which just kind of rearranges chunks of a matrix. There's a definition over there. Don't try and absorb it. And something Carolyn mentions was partial duals. And this is an operation on an embedded graph that's the geometric analog of these PPTs. And every embedded graph has a one vertex partial dual. So you're finally there. So if you've got any embedded graph, what you can do is you can take any one vertex partial dual, read off the matrix, and construct this critical group. And you need to show this is well defined. So what you do, so if you need to show you, if you take a couple of one-vertex partial duals, H and K, you look at their matrices B for each of these, B of H, B of K, and these are representations of the delta matroid. So I know these are going to be related by PPTs, and that gives me a lot of machinery to work with. But I can't lift this machinery off the shelf, unfortunately, because of these, it's largely because I have to add these identity matrices. So the delta matroid theory tells me what to do, but I have to change the argument slightly. And with this equipment, I can then just look at the Smith normal form and see that the invariant factors don't change, so K of G is well defined. And I think my final comment is that, bringing it back more to matroids, is that everything here draws heavily on the theory of delta matroids, and we're just really motivated. A lot of the work was looking at papers of Boucher and Jim's thesis and interpreting, kind of grabbing the results we wanted there. And you might know that the classical critical group is defined for regular delta matroids. So obviously this should hold for regular delta matroids, except it doesn't. So you have this situation where the delta matroid theory is telling you everything you need to do, but it is not actually a delta matroid proof. So this really isn't matroid theory, so rather it's mostly matroids. And that brings me, and I think on that joke I will end there. Not bad.
Thank you, Ian. We maybe have time for one quick question.
So you have described your graph B explicitly. Is there some way to deduce it from the second differential of the cellular complex that your embedded graph defines?
Sorry, I couldn't quite.
Yeah, so is there a way to define graph B via the differential of the cell complex that your embedded graph defines?
I don't know. It very much has a flavor that you should be able to do.
You said like
it
we
really
have
has a
adjacency matrix, then we don't,
homological
but we still
flavor
have.
Yeah, so you can interpret these. So these matrices, you can get hold of them if you look at the homology theory of the and the dual homology and the cohomology, and look at transformations there. So you can get hold of them through sort of Poincare duality. You don't need to. It sort of has the flavor. There should be kind of more homological stuff going on under the bonnet, but I'm not exactly sure what it is.
In particular, maybe it could help to not to care too much about whether you have one vertex or several, right?
Yeah, so in terms of that, because you can take these partial duals, you don't care for that.
I see.
So yeah, so you're taking the partial dual, and you could reinterpret this matrix in terms of the original embedded graph.
Okay, I guess with that, we'll thank Ian again.